This is the first ever image of a black hole, captured by scientists from the Event Horizon Telescope collaboration. It shows the black hole at the center of the galaxy M87 and reveals a ring-like structure with a dark central region, the black hole's shadow.
We have targeted M87, which is a galaxy not too far from here, and its center has what we think is a black hole with about 6 billion solar masses. This makes it very large on the sky, despite the fact that it is far away from us. We have then used a set of radio telescopes, which are distributed on the globe, to receive the light from the center of this galaxy all at the same time and put it together so that we can have a very high resolution, a picture of the black hole with the highest possible resolution. This was not possible before, and it's just the technological advancement of the last few years which have allowed us to do that. The Event Horizon Telescope is an international collaboration bringing up groups from Europe, the US and Asia, in particular Taiwan and Japan. And within Europe, we are part of the Black Hole Camp project. It's an ERC Synergy grant funded by the European Research Council, and I partner with Heino Falken in Nijmegen and Michael Kramer in Bonn. What we do here at the Goethe University in particular is to provide an theoretical understanding and interpretation of the observations. In other words, we try to explain what is it that we see and why it looks exactly like that. And for doing this, we need to perform simulations on different stages. Particularly, we need to perform simulations on supercomputers that tell us how plasma falls onto a black hole.
In the reality, most of the matter does not directly fall onto the black hole. The matter is usually rotates around the black hole. This is similar to the Saturn. It's surrounding around the ring structure. Accretion disk is weakly magnetized plasma, and the magnetic field in the accretion disk is become the turbulent. Then the matter is due to the rotation speed. Then it fall onto the black hole.
So as the magnetized gas is falling onto the black hole, it heats up and therefore generates the light that we then see. Now, from our daily experience, we expect that light travels on straight paths and straight trajectories. We call them rays. Here, the situation is very different. We have a black hole sitting right there, and it's extreme gravity. It is deflecting and bending the light rays away from the straight paths, and it basically distorts the image by a great amount. So, in fact, you can see things that are actually behind the black hole and that you thought were obstructed by the black hole, simply because the black hole is bending the light rays into your line of sight. So if you think about how the image is supposed to look like, you expect that the black hole itself doesn't emit any light, so you expect a dark region, and around that dark region you expect a bright ring of emission coming from all those light rays that are strongly deflected and had plenty of time to move around the black hole and collect the light that we see.
After we computed the radiative signature of our simulations, we have to compare them to the observations. And this can be imagined as you are in a stadium during a football match, and you have an image. And you want to figure out if this person or whatever is on this image is among the spectators in the stadium. So what you do is you take this image and try to match it with all the 60,000 spectators in the stadium. And you do this while you rotate it, you scale it, you increase the contrast, and you try to figure out what is on your image. Is it a person, is it a cat or whatever? And try to match this to the spectators. This seems trivial, but it's not. It's a highly computational, demanding process. So we need a supercomputer, which we have in Frankfurt. And we developed a so-called genetic algorithm, which is a very smart way running through these images and try to adjust them. And this takes roughly a month. And after this calculation time, we have maybe 10 of those spectators which match your image. And this is very similar to what we do in the EHD. So we try to compare and match our observations with the theoretical predictions.
Through the years, people have been proposing also alternative objects that mimic the properties of black holes that are called black hole mimickers. And now with the Event Horizon Telescope, we have for the first time the opportunity to look at black hole candidates closely enough to see whether they are really black holes or they show features corresponding to these other kind of objects. For example, here in Frankfurt, we have simulated accretion onto a boson star, which is one of these mimickers, and we see a flow behavior that is very different from what we expect in a black hole.
Black holes represent for me, as a theoretical physicist, a bit of a no-go area, right? Because there is a portion of them that you can study, but you cannot test. Because whatever tests you carry out inside a black hole, you cannot experiment for an external observer. So for me, this has a very deep sense of fascination. And I was thinking about black holes a lot when I was sailing on a small sailing boat across the Atlantic. And during the night shifts, you had to kill time and, beautiful skies, no light, pollution. And you can see so many beautiful stars. You can see the galaxy, the Milky Way perfectly well. And thinking about there are so many black holes in that environment really was a way of keeping myself awake and avoid falling asleep.
When I first got seriously interested in black holes, I possibly would have hoped that we can image them one day, just because there are so many great scientific achievements in the past that seemed completely impossible at the beginning, but once people got to it, they managed it regardless. But that was perhaps a bit naive. If I had gone into actually making the calculation and figuring out how small those black holes actually are, even the biggest ones we know of, I probably would have thought it's impossible. And so it's really a great technical achievement that we have this capability to make these images.
So the most exciting part of the EHT collaboration is that it's a very large international collaboration, having the leading scientists in both the theory and in observation. And during my work, I learn every day something new, and this is amazing to me.
We teamed up by an excellent group of collaborators that have provided fundamental contribution to the Event Horizon Telescope. So much so that nowadays Frankfurt is worldwide recognized as a leading center for the theory of supermassive black holes.
As a child, I used to read the science magazines where they talk about black holes, and all of this was really fascinating. But at that time, I never imagined that at some point I would actually study them myself. So even when I was studying to become a physicist, I didn't realize I wanted to study black holes until I met a PhD student that was doing his thesis about the shadows of black holes. So he taught me about these shadows and about the very exciting possibility of taking a picture of one of them with the Event Horizon Telescope. And so after knowing that they, here in Frankfurt, they were part of this project, I became very excited, and now I am here.
Yes, I stuck to the problem, so I usually try to solve it for this problem hardly. But if I couldn't get in for the solution, I usually go outside. So here is go to the outside. We see the many nice park around here. I can sit into the park and then to become the relaxed. Then usually I can get in for the very nice idea to get in for solve the problem. Then we back to the office. Then usually we solve the problem.
So black holes actually are very difficult to study. That's why it's been a challenge which has not been accomplished yet.
Goethe University's team of theoretical physicists will continue to search for answers to unlock more of the mysteries of the universe.